Hello, good evening. Good evening, everyone. Thank you, Bharti, for giving me an opportunity to share my knowledge, share some aspects on quantum mechanics, and also thank you, Mr. Rajiv Gandhi, sir, for continuous arranging session for the students of NET and SET. So, friends, today's session is last session on quantum mechanics. Then we'll take another topic or the another chapter. So, as we have seen quantum mechanics for last 5 6 lectures or the 5 6 sessions, and we have learned various aspects of quantum mechanics. And while learning quantum mechanics, we came to know how quantum mechanics emerges and what are the importance of quantum mechanics. And almost I tried to connect you to the basics of quantum mechanics because whenever we want to go ahead for the development of theories or for solving the problem of quantum mechanics, we must remember the basic, we must remember the some of the advances which came out from the application of the basic of quantum mechanics. And that is why in today's session we are just moving, we are moving with where we left in last session. So, as we are going to discuss this particular syllabus, so we learn. Simply, let me recall what we learn from where we have started, we have begin, and then now what we are going to discuss in today's session. So, friends, as we know, the different aspects of the quantum mechanics means how quantum mechanics emerges from the classical mechanics, how there was a shift from classical to quantum, and what was the need behind that. So, initially, everybody knows the need was like when some scientists were tried to explain the black body radiation spectrum, then they observed instead of continuum, they observed some discreteness in the spectrum of the black body, even though as per the expectation radiation shifts their wavelength. And again, that was the reason of we can say the reason of anomaly or reason of some drawbacks of the classical mechanics, and that is why everybody thought for the new kind of mechanics which may gives the answer for this type of the problems. And as we know, the Planck's theory of radiations gives number of answers for that kind of the problem. So that was the first idea. Then again, as we know, when Einstein tried to study the effect we called as the photoelectric effect, then he observed some new kind of the results, and again he was unable to explain this kind of the results with the help of existing physics we called as the classical mechanics. So that was again another breakthrough to enter into the quantum mechanics. Then again, in continuation with that, as we know, the Compton has done the experiment related to scattering. Then again, he has proved some new results. And these are the history or historical backgrounds of the quantum mechanics, which leads to exist some mathematics inside the quantum mechanics. So, and because that was really essential, and that is why we are considering two kinds of the mechanics are related to solve the problems of quantum mechanics. The first one is the wave mechanics, and the second one is the matrix mechanics. So, out of which we were discussing wave mechanics in last class, and we have seen how wave mechanics are utilized to solve the problem like one dimensional potential wave or the harmonic oscillator or the tunnel effect. So these are the problem which we can solve by using the wave mechanics, where we can use the psi as a wave function. And as we know, if we use only psi, then it doesn't have any significance. So that is why we are always multiplying psi by its psi asterisk, and then we call it as a mod of psi square. And if we are talking about that mod of psi square, then we know it is the function of what like a position, that is, as we know, the x, y, z, and the time t. And if we consider that a function psi of x and t, then we know it has some value, or instead of psi, it has, if we are using the mod of psi square or the psi square, then it has some physical significance. And then we can use that particular quantity for solving various problems arise in quantum mechanics. So that we will that we lead again in today's session. But again, let us see. some of the things. As we know, why we are too much interested in quantum mechanics, so the things are very simple, the small things are weird. So if we are just trying to miniaturize, then we can see some anomalies there. As you may be knowing, when people are talking about nanotechnology, so then how they found, so the properties of material at nanoscale are abruptly changing. And then really means the people are wondering why it is changing, how it is changing. As we know, means so this is what kind of the things when we just come down or the chop down to the size of the particle. So that is why the saying is like small things are weird. So and that is why means the quantum mechanics, we can say, having the beautiful explanation for the development of various devices. As we know, the scanning electron microscopy or the atomic force microscopy or the scanning tunneling electron microscopy, these are the microscopies where means with the help of that we can resolve or we can get s- we can get what we can get. Basically we can get solution for so many problems, so that problems can be solved only with the help of quantum mechanics. Otherwise people are talking about nanomaterials and as we know the like nanoscience, but it's very much difficult for everyone to have the appropriate explanation or to measure the appropriate size of the nanomaterial. So if they just try to measure the size of the nanomaterial, then we know, so it's very much difficult to measure the size of particle at nanoscale if we use the optical microscopy. So it's not a easy job. So friends, to and again, if we want to measure, then we know, or the scientists arises, they got some results from the quantum mechanics, and then they have developed the scanning electron microscopy or the scanning tunneling electron microscopy or the atomic force microscopy. And as we know, with the help of this type of microscopy, they were able to measure the size of a particle at nanoscale. And that again, in that way several break so So again, if we go for the quantum mechanics view, then like we can say that so earlier, as we know, so everybody thought it means like light has proved as a wave nature through the wave theory of light, and as we know, the wave theory has given significant results for the different phenomenon like as we know the scattering, then the phenomenon like as we know the scattering, then the interference, diffraction of light, polarization of light. So these all phenomenon were satisfactory explained by the wave theory of light. But again, when there was a shift from classical mechanics to quantum mechanics, then it was it was somewhat difficult to explain how light can behave as a particle when we are just moving from radio waves towards the gamma radiations. So then, as we know, one of the breakthrough in quantum mechanics, like as we know, the Davison and Germer experiment, and with the help of Davison and Germer, when the diffraction of the electron was studied by the Davison and Germer, along with the diffraction of the again some waves. So then they observed the values for the wavelength are similar. So they obtained the similar values, and then again finally they concluded on the basis of that, if light can behave as a wave, then it must behave as a particle. Or if any of the thing or the light can behave as a particle, then it must behave as a wave. And then there was a emergence of the concept of matter waves. And matter waves are the waves, as we know, which are always associated with the moving particle. Okay, if the particle is steady, then we cannot study the phenomenon of the matter wave. So these all are the theories came from the quantum mechanics, and one by one emerges like that. So and again, as we know, the quantum mechanics is considered as a probabilistic mechanics. So as we know, we cannot say everything is perfectly. So we are taking the benefit of probability, and then with the help of probability, we can design some experiments, or we can design some theories, and then we reach to certain conclusions. So this is again like some properties come in dual packages, can't know both simultaneously to arbitrary precision. So as you may be knowing, after the Davison and Germer experiment or the de Broglie's hypothesis, one of the most important scientists came into the picture into the quantum mechanics, like Heisenberg. And Heisenberg has given the uncertainty principle, where he has discussed the phenomenon like that it is impossible to determine the position as well as the momentum of a microparticle with exactness and simultaneously. So it was again, that was the again one of the major breakthrough. So yes, if we consider the microparticle, then it is possible to measure the position, but not the momentum at the same time with the precision. We can measure, but again with certain uncertainty, and that is why he wrote delta x into delta px is greater than or equal to h by 2 pi. So, friends, and again, as we know, that particular principle has given solid evidences for the atomic model. Electron is revolving around the nucleus. So then that particular Heisenberg tried to calculate the energy of the electron when it is moving and all, like, and then he found so the energy of the electron must have some different result, and then on the basis of that results the or the energy radiated by an electron, then he said that the electron means he has confirmed on the basis of Heisenberg's uncertainty principle, electron cannot present inside the nucleus. It must be just revolving around the nucleus. So in that way, some of the things came into the picture. Then again, as we know, this is what a black body radiation, like a expected graph, and this is the classical graph. As we know, you can see how, and again, it's a quantum mechanically or the accepted graph, frequency versus the intensity, and then we can see how good agreement is there. Then again, as I told you, the photoelectric effect. So in case of the photoelectric effect, we know. So when any of the light falls on a metal, then there is a ejection of an electron. And while ejection of an electron, as we know, so how the things are possible. Then again, we can see the some of the problems continued from the classical mechanics, but again, these problems were solved, or the scientists could able to solve this problem with the help of the quantum mechanics. And again, as we know, so then we can say that there is a end of the mechanical age, where we can say ki things move in a continuous manner, all motion both in the large and small exhibits continuity. So that is accepted. Then things move for reasons. All motion has a history, is determinable and predictable. All motion can be determined and can be predictable, can predict. And that is what we know, the Heisenberg's uncertainty principle, which gave some certainty or the evidences. And the universe and all its constituents can be understood as complex machinery, each component moving simply. And a careful observer can observe physical phenomenon without disturbing them. So as we know, if we are just trying to discuss about classical mechanics, in most of the system, we have to disturb the system. But whereas if we are using the quantum mechanics, then there is no need to disturb the system. And that is why here you can see a careful observer can observe physical phenomenon without disturbing them. What does it mean? It means that if you want to take the picture of surface, or if you want to take the morphology of any of the material, then you need not disturb that material, and then without any disturbance you can take the picture of that material with the help of scanning electron microscopy or the scanning tunneling electron microscopy. So that is what the beauty of the quantum mechanics. And inside atoms, all of these statements proved false. So, friends, yes. Then again, what went wrong? Like classical physics could not explain so simply. Just yeah, this is very much important while solving everything. So classical physics could not explain so the electron configuration in atoms, then the black body radiations could not explained by the quantum mechanics. Then again, as we know, so because of these all reasons, as we know, again the photoelectric problem while explaining, so Einstein could not take major help from the classical mechanics, and that is why. So the quantum mechanics emerges. We can say that. Then again, you can see. So we can say that again the specific thermal capacity of a crystalline solid or the Compton scattering of the X-rays. So these were the problems, and again so many scientists overcome with the help of the quantum mechanics. And then because of this, all the quantum theory came into the picture, and we called it the quantum mechanics. And then we have explained these all things in previous classes also. So you can see here, here if we see the bunch of photons, we call it the light, and then simply we can imagine how the image can be seen if we have good resolutions. So here we cannot see the image. Here you can see we can have some traces here, some better traces when we are having 10 to the power 4. Here you can see if we are having 10 to the power 5 photons, so you can see the image. Again 10 to the power 6, again if we go for the 10 to the power 7, which means that it is very much easier to achieve these all kinds of the things with the help of quantum mechanics. So again, how photons travel. So simply we know the photon can be considered as a particle like electron and other neutron. And again, we can, with the help of that, we can assign some properties to the photon. And again, scientists then agreed with yeah, these all phenomena. So it's a basically line spectra, which we have discussed earlier. So just I am moving. Again, here you can see probability waves for the electrons. How STM image you can see electron density waves in coral of 48 iron atoms on a copper surface. How it can be seen on a surface. Then again, simply you can see the molecular spectra that gives us various explanation. Then again, here you can see uh, the photoelectric effect. So simply when light falls on any of the metal surfaces, then there is a ejection of an electron. So but it is always happen at a threshold frequency below which no emission occurs. And again the maximum energy of the electrons is independent of the light intensity, and the photoelectric current is proportional to the again light intensity. Is where the observation Einstein has taken taken about the photoelectric effect. So this is photoelectric effect. You can see simply we can have some equations and we can get the energy associated with that. So that is again important. Then again, so as we know the some of the applications like LEDs and all, so we can see the so here you can see the electron diffraction image, and where we can see lambda is equal to h by p or h by mv. Mv is the equation, and for that you can see how it comes. Then like quantum mechanics or the quantum behavior, not particle behavior, not wave behavior, but we can have the both like a wave as well as the particle nature. when we talk about the quantum mechanics. So again, we can see some of the things. So the stability of the nuclei, we can calculate it. Then again, so these all things can be solved with the help of the quantum mechanics. Now here you can see quantum tunneling. So it's again one of the important phenomena. When we talk about quantum tunneling, then you can see. So when and how the question of quantum tunneling arises. So in case of the quantum tunneling, we must understand if the barrier is having a highest potential than the particle, or the energy of the particle is less than the barrier, then how particle can cross that particular barrier? Then again, here there is only one probability. If we consider that particle as a wave, then we know wave can like a wave has different phenomena. Wave can means like we can see wave can transmit, or the wave can reflect. Waves can means, as we know, the reflection, refraction. So in that way, if we consider any of the particle as a wave, then as we know, the waves or that particular particle can cross the barrier at when the like a potential of the barrier is more as in comparison with the energy of the particle. So in that case also, that particle can cross the barrier. So potential barrier, you can see around the uranium nucleus presented to a alpha particle. Here you can see the potential barrier we have created. The central veil is due to the average nuclear attraction of the nucleons, and the heel is due to the electric repulsion of the protons. You can see here. Alpha particles with energy E trapped inside the nuclear veil may still escape to become alpha rays. You can see here alpha rays, as we have considered as a radiation or the waves, and then because of that it can escape from here, otherwise it is not possible to cross this particular barrier. Alpha rays by quantum mechanical tunneling through the barrier. And again, this kind of the phenomenon has several applications. As I have mentioned earlier, it can be used for making the device like a scanning tunneling electron microscope, or this can be used for making the tunnel diode. And again, it has some different applications for switching on and switching off. So these all are beautiful applications we can get from the tunnel effect, or we call as a quantum tunneling. So again, these kind of the scans we call as a PET scan, with the help of positron emission tomography. We can have only with the help of quantum mechanics. Earlier, it was not possible. So again, just I am moving from this simply. I am not discussing a lot. So as again, we know when we discuss about electromagnetic spectrum, or the size of the atoms or the molecules or the any of the object, then how it will be and where we can use. So simply this also we have discussed. We have discussed about the waves, and again the particle and waves. Here you can see. Simply I want to show you the waves and particle. What do you mean by them? So material objects, you can see particles, they can be located at a space point at a given time. They can be at rest or the moving or accelerating. These are the particles we can see. But waves you can see. Waves is nothing but a ripples, or the surf, or the ocean waves, sound waves, radio waves, as we know, and need to see the crest and troughs to define them. So waves are oscillations in space and time. With respect to, you can see this is the space, this is the with respect to time. So particles and wave, now here you can see the basic difference in behavior. As we know, when particle collide, they cannot pass through each other. They can bounce or they can shatter. But if wave collide, then as we know, there may be the phenomenon of the interference, and through which we can have more intensity. Or so that is what the beauty of the wave. But if we are considering the particle, then they can shatter. They can once collision, yeah, here you can see. So now here there is a collision, and because of collision they are just now how or what will happen with them, we can see here. Another collision we can see. So this may happen if we consider the particle. But now here you can see, if two waves are collide or like coincide with each other, then we can see the resultant. How do we get it? So wave can pass through each other. As they pass through each other, they can enhance or cancel each other. Later they regain their original position. So we can see here, so how their original positions are. So simply you can see here, waves and particles spread in space and time can be superposed, show interference effects and the pass through each other, you can see here. And again, because of this kind of the theory or this kind of the mechanism, so simply we can see this quantum picture of the world is at odds with our common sense view of physical objects. We cannot uniquely define what is a particle and what is a wave. And again, you can see these were the people who just made, who contribute a lot into the quantum mechanics, and only because of them now we can imagine or we can have a tremendous technological revolution. Only because of these people we can say, we can consider, like Neil Bohr, Warner Heisenberg, were the architects of this quantum worldview, along with the Planck, Einstein, de Broglie, Schrodinger, Pauli, and Dirac. So now, just we can see here the true understanding of nature required that physical objects, whatever they are neither exclusively particle or the wave. So we are just accepting sometime it as a particle for our better understanding. Sometimes we can accept it as a wave for our understanding or for our explanation purpose. So here you can see how the electric current flow of electrons. We can see simply here. So again, we can see, I want to just move ahead from this. Okay, so wave nature of matter, already we have discussed this. And here you can see the electron microscope picture of a fly. How fly can be seen with the help of electron microscope. So summary of duality of nature, wave particle duality of physical objects. You can see here light and particles. So finally, quantum mechanics, we are coming to conclusion of the quantum mechanics. So all physical objects exhibit both particle and wave-like properties. So that we have to accept it. This was the starting point of quantum mechanics developed independently by Werner Heisenberg and Erwin Schrödinger. And that is why we are more interested towards the Schrodinger equations, which can solve various problems related to or the associated with the quantum mechanics. And that is what we can see here. So simply again, the one more concept of wave packet I want to introduce here. So this is what we can see, which is moving here. It's not a single wave, it's a wave packet. So when there is a number of photons moves together, or that they can form the waves together, then here you can see they can travel with this. Then again there is spreading position or the superposition of waves of the different wavelength to make the wave packet. So here also you can see the electron. So now how the illustration of the measurement of the electron position, so that we can see in terms of the electron microscopy. Now this is what we can say, we can move. And again, if we go back in a history of quantum mechanics, then we can say that most of the scientists were just discussing, or they have written in some their text. They said at this moment we can accept it. The thing is like that. But if some modifications or if some results may arise as in future, then we can modify our theories also. That is what their thoughts while development of the quantum mechanism. That is why, as you may be knowing, the new theories like a string theory or the chaos theories are still coming into the picture. And then on the basis of chaos theory or the string theory, everybody is saying still there is a certain limitation for the quantum mechanics, and we cannot accept quantum mechanics as a complete mechanics which can solve the entire problem and which can overcome entirely the classical mechanics. So that is why we can say that the still classical mechanics also can be accepted for solving the problems related with the macro particle. We cannot use the quantum mechanics for solving the problem associated with the macro particle. So and now let us see, we are just what we are recalling, like along with this, like a wave particle duality, Schrodinger's equation, time dependent and time independent, then eigenvalue problems, particle in a box or the harmonic oscillator, hydrogen atom problem, then tunneling through a barrier, wave function in coordinate and momentum representations. So simply if we see the wave particle duality, yesterday also we have seen in last sessions. So now the when we are talking about the wave particle duality, then we know simply we cannot forget the Max Planck's works. So the legacy of the Max Planck, and again before Planck, light had been shown to be wave motion. Then light does things that only waves do. So diffraction, this is where light spreads out when it passes through a single slit. And again, simply as we know, again we can have the bending also. If the width of the slit or the dimension of the slit must be comparable with the wavelength of the light, and we can observe the pattern like that. This is a diffraction. Again, the interference, as we know, two waves are interfering on each other, so then the intensity maybe increases or they can cancel with each other, and accordingly, we can have the constructive as well as the destructive interference. So again, that can be proved that has proved with the help of the Young's double slit experiment. But after Planck, you can see, so Planck had found that light under certain circumstances behaved as a stream of particles called the photons, and these particles are as real as electrons. Now here there is a concept of photon, and photon was accepted as like a particle. Then the waves and particle nature of the light are both real. So we need both ideas to explain the behavior of light. And this is what we call as a wave particle duality. Means here from the Planck's view or the Planck's thought, everybody has thought or everybody has accepted to explain light entirely. We required a wave particle duality. We cannot ignore one behavior of the light as a particle, or one behavior of the light, another behavior of the light as a wave. So if we accept in combination light is having a dual nature, then simply it is very much easier to accept and reveal the nature or the properties or the phenomenon associated with the light, and then we can move or we can develop various experimentations in the field of optics. So again, the it was not long before de Broglie's, as we know, de Broglie asked this question: is it possible that tiny particles like electrons could have wave behavior? That was the question. Can we have the wave behavior of an electron? And it was surprisingly answered by some of the experimentations, like as I told you, as I have mentioned earlier, like a Davison and Germer experiment, which proves if like a light is behaving like a wave, or then electron, if we are considering electron, then electron can also scatter, electron can also diffract, and then finally it was concluded or accepted. So there is a duality, and they even have a wavelength? Yes, they have a wavelength, and like Davison and Jarmer experiment calculated the wavelength when electron diffracted or the electron beam diffracts. So here you can see how the electron. So simply the beautiful animation we can see here. So electron is revolving, but when electron revolving, so how the electron radiates the energy, and then that electron radiates the energy, and that energy is in the form of the waves. So that we can see here. Then again, one of the beautiful explanation given by the de Broglie. So he has explained lambda is equal to h by p. So h by p means here we can see, if we see this particular relationship, then here we can see the wave nature. Lambda gives us the wave nature, whereas m is the mass. or the P is equal to mv, that gives us the particle nature, and both are inversely proportional to each other. And that is why we can say that if wave nature is prominent, then this cannot reveal much, or if particle nature is prominent, then wave nature cannot reveal much. So that is why if we discuss about electromagnetic spectrum, then we can say that towards the radio waves we can get more wave nature, whereas towards the gamma radiations we can get more particle nature, and in between that waves and particle, so we are having the visible radiations where we can see the combined effect of the waves and particle. So this is theory lead to the de Broglie to an equation for the wavelength of an electron. Then again, as we know the electron diffraction. So if electrons have a wavelength, then they should behave as a waves under the right circumstances. Then, for instance, they should exhibit effects like a diffraction and interference. So simply we can see some of the pictures of an object with the help of electron microscopy. With the help of diffraction, you can see how beautifully we can capture the picture. So the size of particle is here. We can see the 200 nanometer. So in that picture, and here also you can see how beautifully we can capture the pictures like nano flowers or the nano rods or some of the good kind of the images with the help of electron microscopy. Now another important equation, or the equation in quantum mechanics, is Schrodinger equation, and Schrodinger has given two different sets of equation. One is the time dependent equation, another one is the time independent equation. So Schrodinger has given two different sets of equation. One is time dependent, another one is the time independent equation. And if we see these particular equations, like equation for matter waves, now here we are focusing more on matter waves. We are not focusing on the simple wave. And again, if we are trying to discuss about the matter waves, then we know this psi is the wave is associated with the like a position x and time t. So psi is the function of position x and time t. So again, simply as I told you initially, psi doesn't have any physical significance. And that is why we are always considering mod of psi square. So when we multiplied by its complex conjugate, we call it psi asterisk, then it has some physical significance. And here you can see the del psi by del t. So this is here, if we see the del by del t is the operator operating on psi. Here also del 2 by del x2 is the operator operating on the psi. So seem to need an equation that involves the first derivative in time, but the second derivative in space. So that is what we required. For this is for the time, this is for the space, and psi of xt is a wave function associated with the matter wave. So as before, we can just try the solution of psi of xt. So by knowing this particular function, so by knowing this particular function, we can see like this psi of xt e to the power I kx minus omega t. So we can expect, or we can assume this kind of the function as this type of the solutions. So equation for matter waves in free space is pre-particle Schrodinger equation. Okay, and then with the help of this, we can come across to this equation: I h cross del psi by del t is equal to minus h cross square upon over 2m del 2 psi upon del x2. Again here minus h cross 2m del 2 upon del x2 is the operator. Here also I h cross del by del t is the operator, and we'll see operator sometime. So the Schrodinger, here you can see who has given this equation, and the Schrodinger has given, again, whenever we are just trying to discuss any of the mechanics, then we are always trying to deal with the energy. Our concept is to deal with the energy, and because of that, here you can see the energy, total energy of the system, E of psi is equal to its addition of the kinetic energy and the potential energy, and that is what Schrodinger has tried to solve. And E psi is equal to minus h cross square twice m d2 psi upon dx2 plus v psi. This gives us the kinetic energy. This gives us the potential energy. And now we have to solve this equation to obtain the value of psi. So if we want to calculate the value of psi, then then you can see here like tell us how psi evolves or behaves in a given potential. So analogous to the Newton's equation. And here simply we can see the Schrodinger's equation. So simply this was a possibility argument, not a derivation. So the Schrodinger equation was just plausible argument. It was not a derivation. But we believe the Schrodinger equation not because of this argument, but because of its predictions agree with the experiment. So as always, we are saying when we try to discuss any of the physics, then we know we have certain assumptions, and again the our assumptions are proved with the help of some of the experimentations, and then we can say whatever we have assumed initially, that is right. The same thing happened with the Schrodinger's equation. And again, it was just then proved that there are limits to its validity. In this form, it applies only to a single non-realistic particle, that is one with non-zero rest mass and the speed much less than the speed of light. The Schrodinger equation is a partial differential equation in x and t, like a classical wave equation. Unlike the classical wave equation, it is first order in time. The Schrodinger equation contains the complex number I, therefore its solutions are essentially complex. So unlike classical waves, there are where the use of complex number is just mathematical convenience. So we can have the interpretation of mod of psi square. So as I told you, psi doesn't have any physical significance, but it is multiplied by its complex conjugate like psi asterisk, then it must have the value like a mod of psi square. And the quantity mod of psi square is interpreted as, so that can be interpreted as the probability that the particle can be found at particular point x and particular time t. So if we are trying to speak about one dimensional potential well, then we know if the psi or any of the particle is inside the, or the electron is inside the one dimensional potential well, then what we are considering there is association of the wave function to that electron, and then we are trying to solve the wave function, not to the not we are not trying to find out the position of the electron. So then with the help of with the help of solving the wave function psi, we can say that the exact position of an electron present inside the infinitesimal the height of the potential well is infinite. So then in that case also we can find the position of the of an electron. So simply what about particles that are not free? So simply we can calculate this. So substitute psi of xt is equal to e to the power I k x omega minus omega t into the free particle equation. So by substituting this, we can get this equation, and we can have this form like total energy into wave function is equal to kinetic energy into wave functions. Then for a free particle, whereas we know the V is equal to 0, means the potential energy. So free particle is, so you can see not that. So for a free particle, we can see E is equal to P square upon 2m plus V of xt. And for that, we can calculate total energy E is equal to P square upon 2m, where we can consider V is 0, or the rest mass is like the particle is at rest. So suggest modification to Schrodinger equation. So finally, this equation must be in the form total energy into wave functions is equal to kinetic energy plus potential energy into wave function. Why it is so? Because if the a particle is at a stable position, then it is very much difficult to calculate the association of the wave function with that, and that is why there is a small change, and then the wave function is associated with the kinetic energy as well as the potential energy. And finally, Schrodinger has derived the equation IH cross del T psi. So this is the operator operating on psi is equal to minus H cross square upon 2m del 2 psi upon del x2 V of xt into psi. So this is what we can see the time dependent Schrodinger equation. So we have the time dependent Schrodinger equation, and some of the notes also we can have from this particular equation. So as already we have just shared, this is what this was the plausible argument, not a derivation. We believe the Schrodinger equation not because of this argument, but because of its prediction. I agree with the experiment, and then we can have this particular. Now, another concept in Schrodinger equation is that, as already I have mentioned, we need some operators. So here there is a concept of Hamiltonian operator, and time dependent Schrodinger equation can think of the RHS of the Schrodinger equation as differential operator that represents the energy of the particle. This operator is called a Hamiltonian. You can see, and usually given the symbol H. So, or the H hat. So this is what you can see, H hat. This right hand side minus H cross square upon 2m del 2 psi upon del x2 plus v psi xt of psi is H psi. This is the kinetic energy operator. This is the potential energy operator. And the combine, you can see it's a Hamiltonian. So the Hamiltonian we can use for solving the various problems in quantum mechanics. So here you can see the Hamiltonian is a linear differential operator. Is a linear differential operator operating on wave function. So Schrodinger's equation is a linear homogeneous partial differential equation. So interpretation of wave function we can see here. Psi is a complex quantity. So how can it corresponds to real physical measurements on a system? So simply we can see, remember, photons, number of photons per unit volume is proportional to the electromagnetic energy per unit volume, hence square of electromagnetic field strength. So that is what we can do here. And then as we know the Born interpretations we can do, and simply you can see psi mod of psi square is equal to psi into psi asterisk. What is this? You can see is the probability per unit length, is the probability per unit length, and it is real as required for probability distributions. And then we can have some condition for the normalizations. So an equation for matter waves, the time dependent Schrodinger equation. Earlier we have seen the time independent. Here you can see the time dependent. So del 2 psi upon del x2 is equal to 1 upon nu square del 2 psi upon del t square. So psi of xt is the wave displacement, and this is v basically. V is the wave velocity. Waves on a string. So can we use this to describe the matter? So again we can try the solutions and we can have the some answer. So again here we can see how we can see the observation in non-linear equations. So we can have, this is the usual part, this is the interference terms, use of fringes and all. So the normalization is again one of the most important condition when we discuss about the quantum mechanics. So normalization is integrate over the limit from minus infinity to infinity. So psi of xt mod of psi of xt square dx is equal to 1. So total probability for particle to somewhere should always be 1. Total probability for particle somewhere is always should be equal to 1, and the wave function which obeys the condition is said to be the normalized. Okay, if any wave function obeys this particular condition, then that wave function can be considered as a normalized wave function. So normalizing a wave function, we can have some examples. Particle with an unnormalized wave function at some instant of time. So you can see a square minus x square, minus a less than or equal to x is less than or equal to a, and here psi of xt is equal to 0, mod of x is greater than or equal to a. Again, conservation of probability. So there are certain Born interpretation of the wave function. It's correct. Then integral must be independent. Then we can see here the integral must be independent of time. So integral must be independent of time and can always be choosing normalizing the wave function. So you can see here minus infinity integrate integration of minus infinity mod of psi x t square dx is equal to constant, and the total probability for particle to be somewhere should always be 1. So we can prove that this is true for physically relevant wave function using the Schrodinger equation. This is a very important check consistency of the Born interpretation, and here we can see with the help of that we can write our Schrodinger equation as integration of minus infinity to infinity psi of x t square dx is equal to constant. Then the boundary conditions for the wave functions, we can put the boundary conditions, and then the wave function must be continuous and single valued. This is one most important function of both x and t in order that the probability density is uniquely defined. Then have a continuous first derivative except at points where the potential is infinite. Have a finite normalization integral, so we can define normalize probability, and here you can see how the wave function can be seen. If it is continuous, then you can see x versus psi of x how it will be. If it is discontinuous, how the graph can be. If it is finite normalization integral, then how the graph can be. So these are the like a forms of the normalized wave function. Then time independent Schrodinger equation, already we have seen this. This is the part I h cross del psi by del t minus h cross squared upon 2m del 2 psi del x2 plus v psi x, you can see here. So this part we can solve. Then by just dividing and solving, finally we are coming to this particular equation. So minus h cross square upon 2m 1 upon psi d2 psi upon dx square plus vx is equal to a. Now we can write in terms of this particular a is separation constant. So we have two equations, one for the time dependence of the and one for the space dependence. And we are also determining this particular equation. So we can solve these equations. So once we solve this equation, you can see we can have the t of t, and this only tells us that t of t depends on the energy. It doesn't tells us what the actual energy is, and for that we have to again go ahead, we have to solve some problems, and again solving the time equation. So we can solve this. Then again, the time independent Schrodinger equation already we have seen. So we can solve, or we can relate this lambda is equal to h by p problem, or we can solve these kind of the problems, or we can give solid evidences from that. So where consider a particle of mass m moving with the velocity v along the positive x-axis. Then according to de Broglie hypothesis, the wavelength of the wave associated with the particle is given by lambda is equal to h by mv. And again, a wave traveling along x-axis can be represented by the equation psi of xt is equal to a e to the power minus I omega t minus kx. So in that way, we can represent the wave. And once we represent the wave by using this, so where psi of xt is called the wave function. The differential equation of the matter wave is one dimensional. One dimension is derived as d2 psi upon dx2 plus 8 pi square m upon h square e minus v into psi is equal to 0. And the above equation is called a one-dimensional Schrodinger's wave equation in one dimensions, and in three dimension this equation can be written as, so here we have used the x, y and z coordinates. So therefore del 2 psi upon del x2 plus del 2 psi upon del y2 plus del 2 psi over del z square plus del pi 8 pi square m over h square, so e minus v into psi is equal to 0. So this term can be written as capital del square psi plus 8 pi square m h square e minus v into psi is equal to 0. So this is the time independent Schrodinger's equations. With, you can see here a is equal to e, the space equation becomes. So we can have these space equations, and we can have the solutions for these equations. Okay, so we can solve that. So finally we can arrive to this, and we can have some notes like in one space dimension, the time independent Schrodinger equation is an ordinary differential equation, not a partial differential equation. Just you remember for like MCQ types of the questions. Time independent Schrodinger equation is an eigenvalue equation for the Hamiltonian operator, as we know. This is the h hat we can say. So operator into function is equal to number into function. So we will consistently use uppercase psi of xt for the full wave function TDSE and lowercase psi of x for the spatial part of the wave function. Time and space have been separated. So here, just I wish to end the content of the like a quantum mechanics. So if you have any questions, any queries, if you need more insight about the quantum mechanics, so please do not hesitate to connect with me so that we can solve some queries and we can reach to certain conclusion. Now, let us just recap in 2 minutes what we learn. So, what we learn basically, we learn, although we have started quantum mechanics initially, and we have started how quantum mechanics shift from like a classical mechanics, and what was the inadequacy of the classical mechanics that was unable to give us the solution for some of the problems like black body radiation or the line spectra or the like a photoelectric effect or the Compton effect. And to overcome these all problems, or the to get the solution for these all problems, quantum mechanics arises, or the quantum mechanics came into the picture. And again, because of quantum mechanics, as we know, we could able to solve several problems, and again we could able to develop the devices based on quantum mechanics. And as we know how beautifully devices were developed with the help of quantum mechanics, as we know the devices from scanning electron microscopy to scanning tunneling electron microscopy, or whatever we are witnessing as an evidences of the nanomaterials or the nanotechnology, that is only because of the quantum mechanics. And that is why so we have to say thanks to all the scientists who work hard for the development of quantum mechanics, because around 1900 1900 or the 20th century, it was really difficult for them to explain some new phenomena over the existing phenomenon. Because if we see the existing phenomenon like a classical mechanics, then it was a well established mechanics till 20th century, because that was able to answer almost phenomenon. As we know, phenomenon related with the stellar objects, or the phenomenon related with the moving object, steady object. Then there were Newtonian mechanics, or the Newton's laws has given satisfactory explanation for the motion of an object. Then the Newton's gravitational, like again the gravitational law that also gives some sort of confirmation for different types of the forces and all. So ultimately, it was very much difficult for everyone to to make everybody understood about new kind of the mechanics. But still, our scientist has done great job while developing the quantum mechanics. So friends, I wish you all the best for the study of quantum mechanics. Don't fear for quantum mechanics. Let's try to understand basic of the quantum mechanics and then move ahead for solving the numericals. What we do usually, we are just shifting, or we are jumping to solve the numericals or the MCQ type of the questions from previous years or from any of the book, and where we commit the mistakes. So once you understood any of the physics or any of the subject, then definitely it will be very much easier to move ahead. So I will just at the end I will recommend some book for quantum mechanics. You can use Quantum Mechanics by Arul Das. Very simple, a simple book written by Indian author, but it's good at par with the foreign author. So, like a book written by the Quantum Mechanics by Sheep, or the Quantum Mechanics by Mers Baker, or the Quantum Mechanics by Ghatak and Loknathan. So, these four books we can consider as a crux of the quantum mechanics. And if you just try to reveal some of the phenomenon from this, then definitely you will be able to good quantum mechanics physicist. So another book again along with these four book, the last book I am suggesting, and I will stop here. So the like a modern physics by Arthur Bezer. So he has also explained beautifully quantum mechanics in a very simple language. So with this note, I just thanks Barty for giving me an opportunity to share my ideas on quantum mechanics for the aspirants of competitive examinations. And in particularly, I thanks to Mr. Rajiv Gandhi for organizing a wonderful lecture series through BARTI for the aspirants of the various competitive examinations. So I wish you all the best and thank you so much. Dr. Nilesh Ugemuge is signing off. Thank you.